Okay, so last time we left off approximately around Reynolds averaging, and we had discussed the idea that it's nonsensical, doesn't make sense to say we want to capture turbulence in the instantaneous sense, because that doesn't make sense, because every time you run an experiment you're going to get a different result. So interpreting turbulence should be in a should be done from a statistical perspective. Okay, and therefore we introduced the idea of averaging, which took an instantaneous quantity, could be anything, pressure, density, velocity, anything in turbulent flow, temperature, whatever. Okay, any quantity. This applies for scalars, species, reactants, heat, everything. But right here we're concerned with velocity and pressure. And you decompose it into an average value. We haven't defined what average is yet. But some average, something over time, over space, or an average across experiments, okay? Or you can come up with your own average definition, plus a fluctuation, okay? And roughly, if you take a time average, for example, what I'm showing here is the measurement of an instantaneous velocity in a pipe, okay, over time at a fixed location. So you see the velocity fluctuates around like 5.8 meters per second. And then your average would be this green line, and then your fluctuation would be the deviation from that average. Okay? Now, however you define that average, it needs to satisfy the following properties. Okay? These are the two notations for the average phi bar or brackets of phi. The key property of averaging, and the reason I say this is that there is another procedure called filtering, which doesn't obey the same properties as averaging. So it's important that you remember what we mean by averaging. The average of the fluctuations needs to be zero. That's a key property of averaging. Okay? The average of the fluctuations should be zero. So the way you construct your average, the way you structure your average needs to satisfy this property. Now, you don't know what phi prime is, but we know how to construct the average based on the basic equation over there. In other words, the average of the average needs to be equal to the average. So if you do it that way, then you make the average of the fluctuations equal to zero. That's how you enforce this property. If you take the average of the above definition, you get phi bar on the left, and then phi bar bar plus phi prime bar. If phi bar bar equals to phi bar, then they cancel, and you get phi prime bar equal to zero. Okay? All right. The average of the sum is equal to the sum of the averages. The average of a constant times a field is equal to the constant times the average of that field. Okay? So over here, A and B are fields. They're not constants. Okay? And the average of the gradient of a quantity is the gradient of the average. And this is the most important quantity over here. And that's the average of a product is not equal to the product of the averages. It's actually equal to the product of the averages plus the average of the product of the fluctuations. Okay, so that's a key. That's going to be the source of our problems when we're dealing with turbulence. So when we filter everything, and in anticipation of what we're going to be looking at, this resembles the convection term. You have U grad U, right? U dot grad U, right? And so you have a UU that you're going to take the average of, and that's going to result in terms that are unknown, really. Okay, we'll see what that means in a second. Okay, so several types of averages. We discussed this briefly last time. You can define a spatial average, or a time average, or an ensemble average. The ensemble average is average across experiments. That's my favorite because it retains time and space dependence. Over here, you could lose time dependence depending on the time period over which you took the average. So which makes your equations steady. So when you do an ensemble average, you will get the an unsteady set of equations. Now the next step is to simply apply the averaging procedure to the Navier-Stokes equations. So these are the Navier-Stokes equations, right? And what we can do, we can do one of two things: either substitute U as U average plus U prime and the pressure as P average plus P prime and see what happens, or just take the average of the equations themselves, okay? Both will give you the same answer. It's easier to take the average of the equations, okay? Okay, so we start with continuity. We take the average of the continuity equation. Average of div u is div of average u, which means div of the average is equal to 0. So in other words, the averaged quantity still obeys mass conservation. Now, why are we doing this? Let's step back for a second. What I want now is a working set of equations for the averaged properties of turbulence. And then whatever is left, we're going to figure out what to do with. Okay, so that's why we're doing this now. We said that we cannot solve the equations for turbulence. Are the question very expensive? So instead, let's write all the quantities as an average plus a very expensive fluctuation, okay? And then let's find equations for the average, transport equations for the average that we can solve and see whatever is left we're gonna model. Okay, that's the idea behind turbulence modeling, really. Okay. Now another property, if the average velocity is mass conserving, this also implies that the fluctuating velocity is also mass conserving. That's really simple because u is u average plus u prime. Div u equals 0 equal to div u average, which is also 0, right? Plus div u prime, and that means div u prime is equal to 0. Okay, so I may ask you about these things in the exam and show that, the fluctuating velocity is divergence free. Okay. Okay, averaged momentum equations. We do the same thing. We start with the momentum equations. Now, before we even do anything, which term do you anticipate is going to give us problems? Yeah, del dot uu or u dot grad u, right? The convection term. That's going to give us problems because that's a nonlinear term. The other terms, the average just goes into the gradients, right? Or the nablas, right? Goes into inside the derivative. So we take the average, we get du average by dt plus the average of div uu, that's going to be the problem term, equal minus 1 over rho grad average p plus mu del squared average u. So when you think about, again, solving for the average quantities, well, these are average quantities. We're going to solve for average quantities except for this term. We don't know what to do with this term yet. Okay? So it's not a quantity that is elementary. It's a complex quantity. Okay? All right? So that's what we end up with. Remember, we replaced, I'm using also another notation. I'm replacing the U average with capital values. Okay? With capitalized values, not U bar. So that's another notation as well. Okay? Hopefully this is not confusing. Okay, so what do we do about the convection term? We have div uu, average of div uu, and then the average goes inside the derivative, so that gives us div of the average of uu. Now remember, this is the total velocity field, includes the fluctuations as well. Then we do the decomposition as u plus u prime times u plus u prime. And then you simply carry out the multiplication, etc. Now, what about this term? Div u times u prime. Now remember, this u is an average quantity. Think of it, it's going to come out of the average, right? Because it's an average quantity. Think of it as a constant, okay? With respect, because the average of the average is really the average. So this average comes out, and then you get 2u times div u prime. And div u prime is 0. The div of the average of u prime is 0, okay? And div u prime is 0 as well. So that gives you 0, okay? So this term disappears, and you're only left with this guy. Okay? Div uu, so that's in terms of average quantities, and the only unknown term is this guy. So when I say unknown, I mean the average quantity is unknown, but we can solve for it. Numerically, you are transporting that quantity, so you do your grid and you solve for it. But we don't have any equations for u prime. All our equations are for capital U and capital P, okay? So now we look at the average momentum equations, you get the first few terms, they look exactly like the Navier-Stokes equations, right? You have du by dt plus div u equal minus 1 over rho grad p plus nu del squared u, except that the meaning of u and p, they're average quantities, on average. Okay, they're not instantaneous quantities, turbulent quantities. But then you have this additional term, div u prime. Now, u prime itself is a tensor. Okay, it's got 9 components because you have u prime, v prime, and w prime, and you combine them, you get this tensor, and we call this the Reynolds stress tensor because it turns out to have the same units as stress. Interestingly, although it comes from the convective term, pardon me, which is interesting, but it looks like a stress tensor. Okay, it looks like a stress tensor, and that gives us the Reynolds average Navier-Stokes equations, okay? So we have div u equals 0, and then Navier-Stokes on the average quantities minus this little thing over here, okay? So now we're almost there. We expressed everything in terms of the average quantities, except that we still have an issue. So how many unknowns do we have here? We have u, v, w, 3 unknowns, p, 4 unknowns. And then if this guy is symmetric, so we have 4, 5, 6, 7, 8, 9, 10. 10 unknowns. Agree? Agree? So you have u, v, w, p, 4 unknowns, and then 6 coming from the Reynolds stress tensor, so 10 unknowns. But how many equations do we have? 1, 2, 3, 4. So 3 for momentum. It's a vector. Okay, so it's a vector. And 1 for, so same as before. So really, in reality though, the stress tensor, so I made a mistake. These are not, so these are 3 additional unknowns here, not because they're the product. So it's u prime and v prime that are the unknowns. Okay, so we have really in total 7 unknowns. U, v, w, p, and then u prime, v prime, and w prime. So 7 unknowns, not 10. Okay. So that gives you 4 equations and 7 unknowns. And that's called the turbulence closure problem. If you've heard someone talk about turbulence closure, that's the turbulence closure problem. Is that when we average the equations, we end up with these nonlinear effects of the turbulence that we have no equations for. Okay? We don't know what to do with that term. Okay? And to generalize the notation a little bit, because we called this looked like a stress tensor, okay, so we're going to give it the same notation we did before for the stress tensor, and we're going to rewrite the equations this way. We're going to put the stress tensor, remember our molecular stress tensor, molecular diffusion, looked like div tau, and then we're going to call the turbulent stress tensor div u prime, we're going to call it tau turbulent. Okay? That's the turbulent stress tensor, Reynolds stress tensor. Okay? Now, I'm writing it in this way because that is going to help us think about what we're going to do with turbulence models. Okay? But we still have a closure problem. We don't know what tau turbulent is. Okay? Okay, so how do we solve the closure problem? We either model the stress tensor. Say tau turbulent is equal to tau molecular. Why not? I mean, it looks like a stress tensor. So, and turbulence is in effect a dissipation mechanism. So the effects of the Reynolds stress tensor should be dissipative in nature, and therefore they should be similar to molecular dissipation. So why not model it as something equivalent to the molecular stress tensor? Okay, so that's one model. Okay, or we can develop more equations for the stress tensor. But what does that mean? So we developed an equation for the mean, and that gave us a unknown u prime. Okay. Now, if we develop an equation for u prime, we're going to get an unknown for u prime, and v prime, or u prime, right? We're going to get a triple correlation. And then you develop an equation for that, you're going to get a quadruple correlation and so on. But you will always have the closure problem. So you would have to stop somewhere and say, I'm going to model that term, okay, in the end. It just gets really complex, okay? We're going to go over all of these models. We're skimming the surface here, okay? We're skimming the surface to give you an idea of what turbulence modeling is about. Okay, it's a big field. People dedicate their lives to develop turbulence models. Now, the general, what we adopted generally is in the community are two classes of models, what we call first order and second order models. In the first order models, we directly model the double correlation U prime, U prime. Okay, we directly model that. So although that's a second order moment, if you know some statistics, U prime is a second order moment of the correlation function, okay? But that's what it's called. But we attack it directly, so that's why we call this is the first order attack directly on the second order moment. Now the second order models, they attack the triple moment, the triple correlation, the third order moment, okay? All right, now some nomenclature, there's, in the first order models where we're directly modeling U prime, there's zero equation models that says that directly models U prime. There's one equation models that says, okay, I'm going to write U prime as a function of something, and I'm going to write an equation for that thing. It's going to be kinetic energy. And then there's the two equation models. K epsilon, have you heard of the K epsilon model? No? Okay, so some have. The K epsilon model is just a first order model with two equations. So it directly models U prime as a function of two new quantities, K and epsilon, kinetic energy and dissipation rate. We'll look at it. And then we write equations for the kinetic energy and the dissipation rate. Okay, and we transport those as well. Okay? So it's a hierarchy of models. Okay. First order models. Well, the idea behind the first order models is to directly model the Reynolds stress tensor. Okay? And it starts with the analogy that we just talked about that says, look, Osinesk, I think, came up with that, and then kind of Pranto picked up on it. And they said, well, in general, we understand that turbulence is dissipative in nature. So therefore, the Reynolds stress should probably look like, on average, like the Newtonian stress tensor. And if the Newtonian stress tensor is given by this, tau ij equal mu or nu, dui by dxj, duj by dxi, then why not write the turbulent stress tensor, which is minus rho U prime, average, as some viscosity that is different than the molecular viscosity, a turbulent viscosity, but multiplied by the strain rate. So remember, this measures kind of the average deformation on a fluid element in terms of the average velocities, capital U, which we kind of know, right? Because we have equations for those. So those are part of the unknowns that you already counted, right? U, V, W, and P, the four unknowns. So if we can express U prime in terms of the unknowns that we're solving for, we're good. Then we would close the system. So think about this now. We simply just removed the div U prime, and replaced it with something that has capital U in it. And that closes our system of equations. The only unknown left is what? This constant, or this thing that may vary in space, ut, the turbulent viscosity. And so therefore, the goal of all first order models, so this is for all first order models, so K epsilon, K omega, RNG, K epsilon, whatever you find, all first order models, they use this form for tau turbulent. So this is fixed, but they figured out fancy ways to compute mu t. Okay? Okay, so now when we replace this assumption into the governing equations for incompressible flows, this is what you get. So you still have div u equals 0, and you have the Navier-Stokes equations, except that we augmented the molecular viscosity by a turbulent viscosity. See where we started? Something very complex into something that's quite practical. And this essentially says, look, on average, the effect of turbulence is to dissipate a little bit more. So it's like you're just augmenting molecular viscosity. Okay? Okay. So this is for all first order models. Now, the research within first order models is computing nu t or mu t. Okay? So we start with zero equation first order models. And by definition, the zero equation first order models immediately express mu t algebraically without solving any extra equations. So they give you an algebraic relation, mu t is equal to something. Okay? And this is where Prandtl came in and introduced the mixing lengths theory, which is on average the distance that an eddy travels, like the mean free path, and on average the distance that eddy travels before it diffuses, something like this. And from scaling arguments, nu t is meters squared per second, so that's equal to a length scale times the velocity scale, okay? And the length scale is the mixing length, that's the distance through which an eddy travels as it diffuses, times the velocity scale, and you can go through the paper. They end up positing this form: a mixing length squared times a gradient of the velocity. So this would be a known quantity because we are solving for u. So we would be able to compute du by dy, okay? And the challenge here is just figuring out the mixing length. So we moved the problem from mu t to the mixing length. And the mixing length, there are numerous arguments from boundary layer theory, from maybe kinetic theory, or just from experimental observations, or just making an educated guess. So you can fine-tune that mixing length, for example, and say, look, I wanna test my code to look at the decay of isotropic turbulence. We have good observations on the decay of isotropic turbulence. I'm gonna fine-tune my mixing lengths so that I capture that decay correctly. And you set that value in your code and just apply it, crossing your fingers. In the end, it's just added diffusion, okay? It's just added diffusivity, all right? It doesn't, in some problems it may be really important, but in many problems for engineering applications specifically, you don't care that much, okay? It's just a number. Advantages, this is very easy to implement. It's really fast because you're still solving the Navier-Stokes equations. You just augmented the molecular viscosity by a turbulent viscosity, which is equal to a number times the gradient of the velocity, okay? The mixing length times the gradient of the velocity. So it's really simple to implement. It fits in within any standard code. You don't have to write any new equations, okay? So we can do this from the input file in my code, in Wasatch, okay? Good predictions for simple flows where mixing length can be determined experimentally. The problem is it is incapable of predicting flows where the mixing length varies, like where you have separation or recirculation flows behind blunt bodies, etc. Okay? But, people still apply it there. Okay, so now we go to the one equation. The next level in the hierarchy is to express the turbulent viscosity in terms of another quantity that we transport. When I say transport, I mean a differential equation that has a time-dependent differential equation. So we're transporting, okay? So the one equation models, as the name designates, they want to express, the goal is to express the turbulent viscosity in terms of a quantity that we write an equation for. But we're still first-order models because the first-order model, again, directly models the Reynolds stress tensor, okay? So again, nu t is L times u. That was the mixing length. Okay, so we can improve our guess on the velocity scale using the mixing length. So previously we said u, the velocity scale was L times du by dy. But what if we pick another scale for the velocity? And one quantity is the turbulent kinetic energy. Well, obviously kinetic energy is very important in turbulent flows. So why don't we model the velocity scale as a function of the kinetic energy, okay? And the idea is you write u, the velocity scale, this u, as the square root of the turbulent kinetic energy. And what is the turbulent kinetic energy? Is a function of a scale 1 over 2 u prime. So this is the kinetic energy of the fluctuation, okay? That's what's important here. But we don't know what u prime are, okay, right? We don't care about that. We want to write an equation for k. not for U prime, U prime. We just want to write an equation for K. So what you do, you take the Navier-Stokes equations, you decompose, you multiply by U prime, you spend pages and pages doing that. It's a nasty equation. I'm not going to ask you how to derive it. I wouldn't even want to derive it myself, but it looks something nasty like this. So that's the equation for the transport of the turbulent kinetic energy. So think again what we did here. We said mu is still equal to a mixing length, which we still have to compute somehow from experiment or a guess. But then we're going to replace the velocity scale by the square root of the turbulent kinetic energy. But where do we get the turbulent kinetic energy from? We need an equation for that. Okay, so we write this equation from the Navier-Stokes equations, and it obviously introduces a bunch of new unknowns, right? So you have the P prime, U prime, that's called the pressure correlation, and then Ui prime squared, Uj prime, and then all these kind of crazy terms over there. Anyway, again, we make some assumptions, which I'm not even going to claim I know how they did this, but typically we solve this modified reduced turbulent kinetic energy where you have, again, we're solving for K, so we can solve for K over here. It's an unknown, but it has an equation, and this is the diffusion of the kinetic energy, and somehow the Prandtl number comes in, but all the unknown terms, we lump them into two quantities, a production term, or a pressure correlation term, and a dissipation term. And then we say, we're going to model those two terms using the same gradient hypotheses. Okay, we can spend a semester trying to understand how they come up with these, but it's mostly just based on scaling arguments that just, on average, they just work. Whatever form you assume, as long as the units are okay, you'll be fine, okay? You'll be just fine. So now with these assumptions, we close the this equation, right? Because now we've expressed everything in terms of quantities that are being computed, right? So the dissipation is K to the 3/2 over L, and that's essentially a constant. So you get a bunch of constants over here, and that gives you the one equation model. This is rarely used because it has a very annoying limitation in that the kinetic energy scale is not enough to describe the velocity scale because kinetic energy cannot distinguish between large eddies and small eddies. Okay, what if you have a large eddy that's moving slowly and a small eddy that's moving fast? They may have the same kinetic energy, okay? But one of them is a small eddy, one of them is a large eddy. And the small eddy, but what's the key difference between the large eddy and the small eddy beyond the size is that the large eddy is much slower to dissipate compared to the small eddy. So that leads us to say, okay, how can we account for the difference between large and small eddies? Dissipation. So let's take that velocity scale and write it as a function of kinetic energy and dissipation. Even better, forget about the velocity scale and mixing lengths. Let's directly express the turbulent viscosity, which again, we're after just figuring out what the turbulent viscosity is. It's just a number, it's just a value, okay? That's what we're after. Okay? And again, with scaling arguments, we say in this case that the turbulent viscosity, it can be, so units are consistent here. This is meter squared. This is meter to the fourth per second to the fourth, and this is meters squared per second cubed. So that gives you meter squared per second for UT. This ratio of kinetic energy squared over the dissipation rate, okay, is what the two equation models, and that's the K epsilon model. K and epsilon. And now we've introduced two new unknowns, K and epsilon. So obviously, we need equations for, so by the way, this is the definition, by definition, this is the dissipation rate, okay? The rate at which turbulent eddies dissipate, okay? Just a definition. And that gives us the K epsilon model. So I said now we have two equations. We introduced two new unknowns, K and epsilon. We need equations for those because obviously kinetic energy changes in space and time, okay? And so does the dissipation. And the dissipation is going to be higher when there are small eddies, and it's going to be lower when there are large eddies, okay? But kinetic energy can have the same value for. So with this K and epsilon, we can account for the difference between large and small structures. So these are the equations. There are a ton of approximations that we introduced here, because obviously those are going to have a lot of unknowns, like we've shown for the kinetic energy equation. Okay, I'll give you the slide, so you don't have to worry about kind of writing all of this. But this is the K epsilon model. So on top of continuity and momentum equations, so 4 equations, you solve 2 more equations. These are very easy to solve numerically because they're just scalar transport. Okay, they're just just moving them in time. You have everything on the right-hand side. You advance in time. Very easy to implement. This is the most popular turbulence model in the world, the K epsilon model. You open up, starting a simulation, you have turbulence, turn on the K epsilon model. That's pretty darn good. It's one of the best models out there. Its competitor is the K omega model, but it has very similar similar flavor. Okay, but when you see K epsilon model, just pick the K epsilon model. It's pretty darn good. Okay, it's my favorite turbulence model when I'm doing RANs. So this is Reynolds averaging. Okay, my favorite turbulence model is large eddy simulation, which is something different. We'll talk about. Okay, K epsilon model, easy to implement, always leads to stable calculations. All RANs models are pretty darn awesome. They always converge because you're adding so much diffusion. And diffusion has a stabilizing effect. It just diffuses crazy gradients, right? You have sharp gradient, automatically diffuses. Okay. Good predictions overall. Poor predictions for swirling and rotating flows. Nobody really cares about that. They still use turbulence models, unless you're like designing wind farms and and you're worried about what Professor Sutherland was talking about the other day. So yeah, then you would have to worry about getting into the finer details. It depends on kind of what you're after, right? If you want to resolve the fine details around our drone or the rotors and the blades, you probably don't want to use the K epsilon model. You probably want DNS over there. But if you want to get kind of the average properties of how the flow looks like, just slap on the K epsilon model and you'll be just fine. Okay. A bunch of other flows with separations. Again, that's a problem with the mixing length approximation anyway. Governing equations may be stiff in some regions of the flow, but still, we can use implicit schemes. The kinetic energy approaches 0 near the wall because you're trying to satisfy no slip over there. But there are models for that, near wall models. But all of these are fixable issues. Okay. Other 2 equation models. So we're still with the first order models, which directly model the Reynolds stress tensor as a turbulent viscosity times the rate of strain. Okay. And all of these 1 equation and 2 equation and 0 equation, they try to model the turbulent viscosity. So 0 equation models, they directly posit a form for the turbulent viscosity, mixing length squared times velocity gradient. The 1 equation model expresses the turbulent viscosity as a function of the kinetic energy and writes an equation for the kinetic energy. The 2 equation models, they express the turbulent viscosity in terms of K and epsilon, or K and omega, or 2 other quantities, okay? And write equations for 2 other quantities. Nonlinear K epsilon model, realizable K epsilon model, renormalization, group theory, K omega, etc. All right. Now, some may be interested in scalar transport, so I'm just going to put a slide about this very quickly. So similar to momentum, okay, scalars that are transported by fluid flow. It's very important. So scalars are also affected by turbulent flows, okay? And so think about the velocity as transporting a quantity like temperature. And if the velocity is going to fluctuate, the temperature will fluctuate as well. So as a working model, I'm just going to give you a simple advection diffusion equation for temperature, okay, given in this form. The same way we decompose the velocity into average plus fluctuating, we're going to decompose the temperature into average T. So I cannot use a capital T, right? And lowercase t is reserved for time, so I'm going to use theta for the average, plus a fluctuating temperature T prime. Then you take the average of the equation above, okay? The the problem term is going to be the advection term, right? Because the average is going to go in for all the other terms. And you're going to get a problem here, average of ut, same way we did before, whatever we did before. This gives you u times theta, so the product of the average velocity times the average temperature, plus the average of the product of fluctuations. Okay? So this is identical to what we did before, right? We recovered the original equations, except the meaning of the terms is everything is average, and we added a term that showed up because of turbulence. Okay? So this term is unknown. So how do you think we should model this? Okay, sure, yeah, directly, yeah. That's one of the most popular ways of doing. Even with a two-equation model for momentum, we just model this directly. But what is that model going to look like? So in the momentum, we said the Reynolds stress mimicked diffusion, right? Mimicked the Newtonian stress. So think of this as something similar to that. What is the effect going to be? Is it going to be similar to this term, do you think? Yeah. That's the same hypothesis, is that just like for momentum, the Reynolds stresses represent diffusion. For scalars, this unknown term, the stress equivalent for scalars, is also a diffusive process. So why don't we model it just like a Fourier diffusion term, or called the gradient hypothesis? And then we say, okay, u prime, t prime. So remember this term is div alpha grad theta, right? That's kind of the standard if you have nonlinear diffusion coefficient. You write it as div k grad t, right? So then this div of this term, so what if we model this term as a turbulent diffusivity times the gradient of the average? And that's how we close the system, okay? And typically, so then when you substitute this back up here, and you assume alpha t is constant, then you get an augmented molecular diffusion, alpha plus alpha t del squared theta. Same idea, same concept. Is it starting to ring a bell? We could have set out by saying from the beginning, hey, we're going to model turbulence, we're going to solve for the average quantities, and then we're going to augment molecular diffusion by a turbulent diffusion, okay? Now, how do we compute this? Well, the reason we don't need fancy models over here is that we can relate the turbulent diffusivity to the momentum diffusivity via the Schmidt number. And then the way you do this, you're spending a lot of effort to compute the turbulent diffusivity. Then you set a Schmidt number, 0.71, and then from that you back calculate the scalar diffusivity. Okay? Second order models, very complicated and annoying. I'm not even, we don't have enough slides to put the equations down. Or like 20 pages for the Reynolds stress model, really complicated. But the idea is, rather than directly modeling the second order moment, u prime, let's write a transport equation for it. That is going to give you a triple correlation, ui prime, uj prime, uk prime, which is unknown as well. So we would have to either write an equation for that, so that makes us a third order models, or model that triple correlation. And that is much, much harder to think about. Okay? The problem with this approach is that you get the number of partial differential equations you have to solve just explodes. Okay, and I don't see anyone using this beyond academic circles. Fluent has a Reynolds stress model. I don't think anyone even kind of cares about using it. But the beauty of the Reynolds stress model is it captures anisotropic effects. That's been proven. So if you care, so what are anisotropic effects? So, naively, isotropy is wherever you look, you see the same thing, right? Things on average are the same. Like the universe is isotropic. You look in that direction, there are stars, galaxies, supernovas, black holes. You look in that direction, stars, galaxies, supernovas, black holes, right? But anisotropy is like you're in a piece of wood, for example. If you look in one direction, the fibers are aligned that way, and you look the other direction, it's all wood everywhere, so it's homogeneous, but it's anisotropic. So if you apply tension to the wood that way, it's going to break much easier than if you like take a 2x4, you get two clamps, you can break it that way much easier than trying to break it if you're aligned with the fibers. So that's an anisotropic material, okay, from the perspective of the stresses, okay? So same thing, turbulence is generally anisotropic. You know, you look in different directions, you're going to have gradients are going to be different, you're going to have different length scales. So however you define, you think of anisotropy, turbulence is generally anisotropic. So the Reynolds stress model will capture this anisotropy. And, you know, you write an equation for the second order moment, but then you're going to end up with terms that have the third order moments, and then those need modeling. So in second order models, you model the triple correlation, or you write one equation models for those, or two equation models for those, okay, and so on. In third order models, you write an equation for the third moment, right, and then model the fourth moment, and so on. Reynolds stress model is very expensive, but like I mentioned, it's one of the classic turbulence models. And I have 6 minutes, and I will introduce you to my favorite and kind of the up-and-coming turbulence approach, because it's become much cheaper and easier to compute because of processing power. So as we move into more processing and cheaper computing, we're moving away from turbulence models because it becomes easier to capture more of the turbulence, right? So ideally, if we have very fast computers, we can just solve, we don't need 5,000 years, right, to solve flow in a channel or a pipe, right? So you can compute all of that. So the large eddy simulation is kind of the first step towards full DNS, full direct numerical simulation, okay? Large eddy simulation. Okay, so the idea behind large eddy simulation is, well, you know, we have a grid. Why do we, if you remember that energy spectrum that I showed you in the past, we said that Reynolds averaging, they model the entire spectrum. They model all scales, everything, okay, from the large to the small scales. In DNS, we compute everything, so you have to have a very, 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 very fine grid. In LES, we compute some and model some. And so the idea is, well, I have a grid, and I can compute things on the grid. Why don't I compute everything turbulent that grid can capture? So all the eddies that can be captured by that grid, and then model everything that cannot be captured by that grid. So remember the eddy drawing I showed you the other day? So let's compute the smallest eddy that can be computed on that grid. Just solve the full equations there. And anything below that, let's approximate it. But how do you make that separation? With averaging, we said, hey, we're going to take an average and we're going to solve the average equations. But with this idea, how do you make the separation between the scales that are computed by the grid and the scales that fall through the grid? So we're going to talk about this. So in LES, we compute everything that the grid can capture, and anything below the grid resolution is modeled, okay? For things to be meaningful, obviously the grid resolution needs to be large enough to contain, certainly larger than what's required for, or the grid resolution needs to be small enough. In other words, the number of grid points needs to be larger than what RANs can do, because you want to compute. Think of yourself moving along the spectrum of kinetic energy. You want to compute as much energy of that spectrum as you can. So you want to compute as many small scales as you can, and then model everything else. Okay. Now, to separate between the scales that can be computed and the scales that are not computed, we introduce the idea of the filter. Okay. Now, I'm not defining the filter yet, because what's more important to realize is the properties of the filter rather than the filter itself. In the end, the grid is your filter. Okay, in the end, the grid is going to be your filter. Now, filtering looks this identical to averaging. You take a turbulent quantity, you write it as a filtered quantity, So that's the quantity captured by the grid, plus the quantity that was not captured by the grid. Okay, same concept. Now think of filtering as a sieve. Okay, the finer your sieve, the more you can capture, the more pebbles or stones you can capture, right? The coarser your sieve, the less you're going to capture. Filtering is the equivalent of the sieve. It's going to capture things that fall are larger than the sieve width or the filter width. So that introduces the idea that a filter has actually a length scale that allows it to capture all quantities that are larger than that length scale, and everything below that length scale disappears. That's why the idea of the filter is important. It's a sieve. Think of it as a sieve. This is actually, I'm glad, it looks like a grid. This is like a structured grid, literally like a structured grid. Any eddy that is smaller than the sieve size is going to pass through, and it's going to be a phi prime. Okay? Okay? More important than the filter definition is the properties of filters. A filter should not change constants. It should be linear in that the filter of the sum is the sum of the filters, just like an average. But it should commute with derivatives as well. So the filter of a derivative in space or time is equal to the derivative of the filter. But the most important properties of the filter, so right now it looks like identical to an average, right? Except for one property, and that is the filter of the fluctuation is not equal to 0. With Reynolds averaging, the average of the fluctuation was equal to 0 because we put think of it as putting the average in the middle of the fluctuation, positive and negative, and then when you take the average of the fluctuation, you add them all up, you integrate, that gives you 0. The filter is different. The filter is saying, no. My fluctuation, the filter of the fluctuations is not going to be 0. Now think about it. If you have think about it in terms of a sieve. You have a sieve of a certain size, let's say, delta, sieve of size delta. You filter out all the quantities that are larger than delta. Anything smaller than delta goes through. Now apply a filter to whatever went through. Is it going to be caught or is it going to go through? It's going to go through because the other filter is still the same delta. And those quantities are smaller than delta, then they're going to go through, So the filter of the fluctuation is not 0. Right? We don't know what it is. Okay? That's actually what we're going to have to model. Okay? Unlike Reynolds averaging, where the average of the fluctuation was identically 0. So with averaging, there's no idea of the sieve. It's just taking, putting something in between the positive and negative fluctuations, and then they add up to, in a way that they add up to 0.